In our next section of Chapter 10, Section 7, we're going to be looking at two additional types of tests about series convergence, specifically the root and ratio tests. We now consider two additional convergence tests for general series, the ratio test and the root test. Both tests are used frequently throughout the next chapter. As in previous sections, these tests determine whether an infinite series converges, but they do not establish the value of the series. The tests we've developed so far determine whether a series converges are powerful, but they all have limitations. For example, the integral test requires evaluating integrals, and it is difficult to use with a series such as 1 over k factorial, because integrating 1 over k factorial is problematic. Furthermore, the integral test and the comparison tests work only with series that have positive terms. So let's look at Theorem 1020, the ratio test. This significantly enlarges the set of infinite series that we can analyze. It can be applied to any series, though its success depends on evaluating the limit of the ratio of successive terms in a series. The conclusions reached by the ratio test rely on the idea of absolute convergence and Theorem 1019 from section 10.6. We assume that a sub k does not equal 0 for all k, so that the ratio a sub k plus 1 over a sub k is defined. So here we let a sub k be an infinite series, and we let r equal the limit as k goes to infinity of a sub k plus 1 over a sub k, the absolute value. If r is less than 1, the series converges absolutely, and therefore it converges. If r is greater than 1, including r equals infinity, the series diverges. And if r equals 1, the test is inconclusive. So there's a proof in your book, but this is it gives you some ideas and some insight. You can walk through it. It's a very short paragraph, but it's really talking about what we're looking at as the tail of the series. Okay? So let's look at some examples to see how we can apply the ratio test. Use the ratio test to determine whether the following series converge. Part A is the sum from k equals 1 to infinity of 10 to the k over k factorial. Now I put the ratio test down here so we have that handy in green. And just to remember about factorials, right, that k factorial equals k times k minus 1 factorial, right? So if this was 10 factorial, this would be 10 times 9 times 8, so it's 10 times 9 factorial. And by that same idea, k plus 1 factorial equals k plus 1 times 1 less than that, which would be k factorial. And these can be helpful in rewriting the limit of a sub k plus 1 over a sub k, specifically so that we can eliminate similar terms that are in the numerator and denominator. So let's look at this first one, and I'll take you through that. Okay. So here all we're going to do is we're going to put a sub k plus 1. So wherever we have k, we're going to make it k plus 1. So in the numerator we have 10 to the power of k plus 1 over k plus 1 factorial. In the denominator we just have the original function, 10 to the k over k factorial. Okay. Well, when you have a fraction divided by a fraction, this is the numerator times the reciprocal of the denominator. Okay. So when we do that, we get 10k plus 1 over 10k. The k factorial goes in the numerator, and the k plus 1 factorial, which becomes k plus 1 times k factorial, goes in the denominator. And then we can see the terms that we can cancel out. For example, the k factorials can cancel out. Notice here, 10 to the k plus 1 is 10 to the k times 10, right? 10 to the k plus 1 is 10 to the k times 10. So the 10 to the k's cancel out, and we're left with 110 left. Because remember, when you multiply exponentials with the same base, you add their exponents. So we can change the numerator here to 10 to the k times 10 to the 1, or just 10. And so that's how we get this simplified expression here, 10 over k plus 1. And of course, as k goes to infinity, this value equals 0. And by our theorem, if r is less than 1, the series converges. So this series converges by the ratio test. Okay, let's look at part B. This one's a little more complicated. So again, we're going to do the same thing. In the numerator, we're going to change all of the k's to k plus 1. So we have negative 1 to the k plus 1. Notice we have k as a base, so that becomes k plus 1, as well as the exponent, which is k, becomes k plus 1. And this is all over k plus 1 factorial. The denominator is just the original function, negative 1 to the k to the k over k factorial. So this one's a little more complicated, and they just jumped from here. So I thought I'd take you through some of the steps. So again, similarly that we did in part A, it's the numerator times the reciprocal of the denominator. Okay, and so that's all I've done here is just rewritten this so we can see it a little bit clearer. I then actually did that step that I was verbalizing about over 10 to the k plus 1. So negative 1 to the k plus 1 is negative 1 to the k times negative 1. Okay. And then we have k plus 1 to the k plus 1. So this is k plus 1 to the k times k plus 1. Again, we can combine these by adding the exponents. When you multiply two bases with exponents, the same base with exponents, you just add the exponents. And then the denominator, we get k plus 1 over k factorial. And then here we have the same thing. So now we can go through and kind of cancel out. I can't even see where I am. Hold on. So I can see the negative 1 to the k cancels out. Let's see, what else do I have? I have a k plus 1 here and a k plus 1 here. I have a k factorial and a k factorial. And so what I'm left with is k plus 1 to the k, this term here, a negative 1, and a k to the k. And that's what they've done here. So we have k plus 1 to the k, a negative 1 in the numerator, and a k to the k in the denominator. Now, why did they take out the negative 1? Well, remember that what we're taking is the limit of the absolute value. So that negative 1 just disappears because of the absolute value sign in the original function. Okay? And then since the numerator, k plus 1 to the k, and the denominator, k to the k, are both raised to the same power, we can pull the exponent out in front. And so this simplifies if we separated this into two fractions, k over k, which is 1, plus 1 over k, all to the power of k. Now, you may not readily remember this, but this is from Calculus 1, and this is an application of L'Hopital's rule in solving derivatives, okay? I mean, solving limits and using L'Hopital's rule, all right? And again, we can see here, because e is greater than 1, the series diverges by the ratio test. It's also interesting to know, we could have noted that the limit as k goes to infinity of k to the k over k factorial, which is the original function, equals infinity, which was theorem 10.6, and use the divergence test to reach the same conclusion. So let's look at our last problem here. C is negative 1 to the k plus 1, e to the negative k times k squared plus 4. Okay? So here they've automatically taken out the negative 1 since we're doing the absolute value. And we have, again, the numerator is every k, e to the negative k plus 1 in parentheses. It's not negative k plus 1, it's negative the quantity of k plus 1. Again, we need to change k squared plus 4 into the quantity of k plus 1 squared plus 4, all over the original function minus the negative 1 because we're taking the absolute value. Okay? So again, here we can see this is e to the negative k, e to the negative 1. Multiplying this out, foiling this out, we get k squared plus 2k plus 5 by adding the 4 over e to the negative k squared plus 4. Well, here the e to the negative k's cancel out. The e to the negative 1 isn't going to change, so they pull that out in front. Because this is a constant, remember, we can pull the constant out in front. And then we take the limit. Well, since the highest power is the same in each, the limit as k goes to infinity is the ratio of their coefficients, which is 1 over 1. So we get 1 times e to the negative 1. Well, remember, a negative exponent means to reciprocate. So this is 1 over e, which is less than 1. So again, by the ratio test, the series converges absolutely. As we've seen in the last example, the ratio test is conclusive for many series. Nevertheless, observe what happens when the test is applied to the harmonic series 1 over k. R equals the limit as k goes to infinity of a sub k plus 1 over a sub k, as we know from the ratio tests, and then applying the limit as k goes to infinity. So here we get 1 over k plus 1 over 1 over k, which gives us k over k plus 1, which when we apply infinity to that, we get this equals 1, which according to the test, it's inconclusive. We know the harmonic series diverges, yet the ratio test cannot be used to establish this fact. Like all the convergence tests encountered in this chapter, the ratio test works only for certain classes of series. Theorem 1021, the root test. The root test is similar to the ratio test and is well suited to series whose general terms involve powers. Theorem 1021, the root test. Let the summation of a sub k be an infinite series, and let rho equals the limit as k goes to infinity of the kth root of the absolute value of a sub k. If rho is less than 1, the series converges absolutely, and therefore it converges by theorem 10.19. If rho is greater than 1, including rho equals infinity, the series diverges, and if rho equals 1, the test is inconclusive. So you can see the similarities here as we've done before, but now what's happening is we're applying the limit as k goes to infinity of the kth root of a sub k, of the absolute value of a sub k. So let's look at example 2 using the root test so you can see how to apply the root test. And again, I've put it in the bottom right corner. I'm not sure if it'll get covered up by the solutions or not, but at least you can see there. The main things are we're looking for rho to be less than 1 for convergence. If it's greater than 1, divergence. And if it equals 1, we don't know what the hell's going on. Okay, so use the root test to determine whether the following series converge. And remember, the test is the limit as k goes to infinity of the kth root of a sub k. All right, so here a sub k is this whole formula inside raised to the power of k. All right, so if we apply the limit as k goes to infinity of the absolute value, or excuse me, the kth root of the absolute value of this function, notice that what happens is that basically we are losing this power of k on the function and just getting the interior or the base of that exponential. So we get, because if you take the square root of anything squared, if the root and the power are the same, of course they just cancel out. So we're taking the limit as k goes to infinity, and of course we're looking at end action, what's happening as we go to the outer edges of our functional graph, and the leading terms are taking over. And since we have the same power in the numerator and denominator, the value of this limit is going to be the coefficients in front, or 4/7. Okay. Now, they also explain why they switch the orientation here. Notice as soon as k gets above 1, this is going to be a negative term. But if we just switch the order, then it will always remain positive, and which is what the absolute value is going to do to it anyway. Okay? And again, since rho is less than 1, the series converges absolutely. When we look at the second problem, the summation of negative 2 to the power of k over k to the 10th, if we take the absolute value, that of course is going to remove the negative. And again, we have, well, this is a little bit different. So we have the kth root of the numerator raised to the k power, so that cancels out, because technically what we're doing is, remember when you have a root or a radical, the exponent is of the function inside of the radicand is the power inside divided by the power of the root. Okay, so this is k over k, or 1, so we just get 2 to the first power in the numerator. In the denominator, we have k to the 10th, so this is going to be k to the 10 over k. Again, that's just using knowledge of radicals as exponents and applying that. So we get the limit of, as k goes to infinity, of 2 over k to the 10 over k. Now, notice what's happening here. Oh, here, this is even better, actually. K to the power of 1 over k, as this goes to infinity, this is k to the 0, right, which will be equal to 1. And 1 to any power is still 1, so we have 2 over 1, which is 2. And that's talking about it there. Okay, even if we left it as 10 over k, as k goes to infinity, this is getting, the exponent is getting closer to 0, and we get 2 over 1. Okay, and again, by the root theory, if rho is greater than 1, then the series diverges by the root test. Okay, we could have used the ratio test for both series in this example, but the root test is easier to apply in each case. And that, remember, we said that the root test is good to use when you have exponents. Okay. In part B, the divergence test would lead to the same conclusion. So try some of the problems now, and we'll move on to the next section.